This is the Geology of the National Parks lecture for Week 8, Topic 2, all about coastlines. Humans love to live on coasts, and coastlines are some of the most beautiful parts of the world. They occur where land, the continent, meets the ocean. This is called the continental margin, the edge of the continent. The margin is the edge of the continental crust, where it meets oceanic crust or another tectonic plate. There are two basic types of continental margins. An active continental margin is the edge of a continent at a plate boundary, or near a plate boundary. You find these at convergent boundaries where there's a subduction zone. They also occur at some transform boundaries, such as along California's coast along the San Andreas Fault. And they occasionally occur at divergent boundaries, only during the initial stages of rifting apart a continent. So, for example, the early stages of the Atlantic Ocean, when it was first opening as Pangaea was breaking up, could have been considered an active margin, because there was active faulting and deformation of the continental crust during the process of Pangaea breaking apart. Most of the west coast of the United States is an active continental margin. The east coast today is a passive continental margin, which is a continental margin away from tectonic boundaries. Active margins are tectonically active, with lots of earthquakes, many volcanoes, and oftentimes high topographic relief. So the coast of Oregon is a great example of an active continental margin. A passive continental margin, for example the east coast and Gulf Coast of the US, are generally tectonically stable with very few earthquakes, no volcanoes, and very thick sedimentary deposits on top of older continental crustal rocks. On both active and passive continental margins you find submarine canyons. These canyons in the edge of the continental shelf are the result of continental sediments scouring out canyons, as well as underwater currents and underwater landslides. But in passive margins, these submarine canyons are usually shallower, longer, and have thicker deposits of sediment. On an active margin, they're usually pretty short and pretty steep, and oftentimes will terminate into the subduction zone trench between the continent and the ocean crust. Passive coastlines usually have long, continuous beaches, a wide continental shelf, and generally a low-relief coastline marked by marshes and estuaries. We can see some pictures here from the United States East Coast, as well as Cumberland Island National Seashore on the right. On the other hand, active coastlines or active continental margins, you tend to have smaller, what we call pocket beaches, a narrow continental shelf, and the beaches often end in tall, rocky cliffs. Oregon, again, a great example of this phenomenon, as are parts of Washington, as seen on the right in the coastline of Olympic National Park, where we have this rugged coastline dominated by cliffs, some coves with rare beaches exposed at low tide. Many people use the words coast, coastline, shore, and shoreline more or less interchangeably. The technical definitions are not consistent. If you look between different textbooks, different dictionaries, different resources, you'll probably find different definitions. The textbook we use for this course defines them as the coast or coastline includes all parts of the land to sea boundary area that are directly affected by the sea. This includes land far above high tide and well below normal wave base. But the shore or shoreline itself is the direct interface between water and land that moves with the tides and with deposition and erosion of sediment. So the shoreline is the edge of the water, and the coast is the whole region. The shore zone, which is that interface between land and water, can be divided into roughly 4 areas. The offshore area is always underwater, but usually affected by turbidites, underwater landslides, as well as deep ocean currents. The nearshore area is the area affected by ocean waves, so this is still underwater, but the sediments are routinely disturbed by large waves during storm events. The foreshore is the part of the shore that is underwater during high tide and exposed during low tide. This is also called the intertidal zone. And finally, the backshore is the part of the shore that stays dry most of the time, but can get flooded during storms or extremely high tides. These different diagrams on this slide are very complicated and show different ways of subdividing the coastal area into different regions. We'll go into some of these terms soon enough. What do we mean first by sea level? The sea level is the average height of the ocean's surface, basically halfway between mean or average high tide and mean low tide. However, for elevation and topography reasons, sea level is defined a little bit differently and may not equal the average height of the ocean at any given location. However, it is that average location of the sea that we define as sea level with regard to beach and coastal processes. Sea level is affected by tide, and tide is the rise and fall of the ocean level during the day due to the gravity of the moon. We see a diagram of that in the upper right here, where the moon's gravitational pull actually bulges out the ocean water and creates a rising and falling action of sea level over the course of the day. The tidal reach is the difference between ocean level at high tide and low tide. The intertidal zone is the region submerged during high tide and exposed at low tide. Finally, a tidal flat is what you get when you have a broad intertidal zone that occurs when the slope of the shore is very gentle and/or the tidal reach is large. So on a steep-faced beach, you might have an intertidal zone that occupies maybe 30 feet horizontally and rises and falls 3 or 4 feet vertically. But a tide flat might be a couple hundred yards wide, or even larger than that, even though it sees the same tidal reach over the course of the day. Again, the shore is the boundary between water and land. Erosion, transport, and deposition of sediments is done by water waves and currents. In the ocean, a wave is an oscillating disturbance of water, usually generated by wind against the water's surface. Waves are usually characterized by wavelength, the distance between two equivalent parts of two waves, the crest, which is the highest point in a wave, the trough, which is the lowest part of the wave, the height, which is the difference in height between the crest and the trough, and the wave speed, which is the velocity that that wave is propagating through the water. Most waves are formed by wind blowing against the surface of the water. This makes a circular motion within the water that we call orbitals. The largest orbitals are at the surface and encompass most of the body of the wave, and then you have smaller orbitals beneath that that extend down into the water. The depth at which the wave is no longer affecting the water is called the wave base, and the wave base is defined as 1/2 of the wavelength. So in these waves, actually you don't see very much lateral motion. The water is not moving with the waves as much as it is going in a circular motion underneath the wave. So the wave is just an energy wave that is moving through the ocean and moving the water in these circular orbital fashions. In the open ocean, we call waves swells, and they only become waves when they reach the beach. Waves break against the beach when the base of the wave, which is oscillating, touches the ground and starts to slow down, while the top of the wave continues to move forward. So as your wave approaches the shore, the wave base will begin to drag along the seafloor, which causes the base of the wave to slow down and the top of the wave to keep moving at the same speed. Eventually, it starts to sort of topple over. It piles up and topples over, and that's when your wave breaks. The surf zone is the zone near the beach where water itself, and not just the wave form, actually moves forward. So offshore, the water is just moving, oscillating in this circular motion, and it's only in the surf zone where your waves are breaking and water actually begins to move forward against the beach. When your wave breaks, the water washes up against the beach. Water moving forward up the beach is called swash, and water moving backwards back toward the ocean is called backwash. It is this action that moves sand over short distances by swash and backwash. Whether sediment is deposited or eroded on the beach depends in part on the energy of the waves. Seasonal variations like storm frequency can either build up or erode a beach. In the Northwest, for example, during summer, we tend to have smaller, more gentle waves. And that means our swash is greater than the backwash, so sand is carried in towards shore and the beach is built up. During the winter, on the other hand, we have frequent powerful storms. So we have larger, higher waves that bombard the beach with high amounts of energy, which makes our backwash very strong, and that carries sand out away from the beach and builds it up in offshore sandbars. So what is a beach? A beach is a dynamic landform made of small, loose sediments found next to large bodies of water, such as oceans or lakes. The appearance of beaches, controlled by waves, currents, and weather, is constantly evolving. Some areas of a beach will gain sediment, causing the shoreline to accrete, while other areas will lose sediment, causing the shoreline to erode. Common features along beaches are bluffs, which are the high, steep banks or cliffs at the back of the beach, dunes, or accumulations of wind-blown sand on the back shore, the shoreline, the line between water and the exposed beach, and the surf zone, the portion of the nearshore area where waves begin to break. This extends into the swash zone. The anatomy of the beach can be seen in this diagram on the left. A couple other features include bars, which are offshore ridges or mounds of unconsolidated sediment that is usually submerged. You often find sandbars at the mouth of a river or estuary, or lying parallel to and a short distance away from the beach. The berm is the nearly horizontal portion of the beach formed by deposition of sediment from the waves. And the trough is the elongated depression extending parallel to the shoreline, usually between the beach and a sandbar. You often find the trough in the main area where waves are breaking. Back to the movement of sand along the beach, generally, backwash is perpendicular to the shore. The water washes up and then washes straight back down. But the swash, on the other hand, is not perpendicular to the shore, so sand particles end up making a zigzag motion along the shoreline, a process that is called the longshore current. So waves rarely come straight on against the beach. They usually come in at a slight angle. So as that happens, your water will wash up, the swash will go up the beach at that angle. It will then drain straight down the beach face, powered by gravity, back directly towards the water. So you get sand washed up, pulled straight down, sand washed up, pulled straight down, and over again as that sand will then move along the length of the beach. An interesting thing that waves do is refraction. The waves are actually bent as they drag along the bottom, when they reach the bottom in an uneven or not straight-on sort of a fashion. They actually bend to near parallel of shore. You can see a few examples of that here. Waves are usually long and continuous, so one portion of your wave can actually drag on the seafloor before another portion of your wave does, and that causes them to bend or refract. And we can see that in this Google Earth image of the Olympic coastline on the lower right. The waves are coming in this direction, almost oriented due north to south. As they approach the shore, they are bent, for example, by these rocks offshore. And then as they get even closer to the beach, they are bent further to become nearly parallel to the shore. And this is the process of wave refraction, and it guides a lot of different coastal processes. The combination of wave refraction and longshore current builds up different depositional formations along the coast. Among these are sand spits and baymouth bars. A recurved spit is a type of sand spit that is just highly curved at its very end. These are some examples of recurved spits showing that highly curved end. This one on the lower left is somewhere in the United Kingdom, and on the right we have a recurved spit outside of Lincoln City on Silet's Bay. Here's a couple more examples from around the globe. We can see this baymouth bar blocking off the front of this tidal estuary here, as well as over in the middle of the image, a sand spit forming coming off of this little headland here. These are both deposited by longshore currents depositing sand along the shore. One of my favorite coastal formations, and the new featured word for this lecture, is the tombolo, which is a narrow strip of land connecting an island to the shore. These are built up as waves are refracted around an offshore rock or island, which reduces their energy and allows them to deposit sediment instead of eroding it from the area behind the island. Over time, the area of low wave energy behind the island creates something called a wave shadow, and that allows sand to build up and create a tombolo. You can see one here from the central California coast, where there are actually quite a large number of tombolos. Additionally, coastal movement of sediment is governed partly by human structures. Among these are breakwaters, groins, and jetties. These disrupt sand deposition along the shoreline, sometimes intentionally, sometimes accidentally. On the left, we see a series of breakwaters. These serve to reduce the energy of waves coming into the shore. You can also see that because they reduce the energy of incoming waves, sand is built up behind these breakwaters. A jetty will extend out from a harbor or estuary entrance, which reduces the wave energy inside the mouth of the harbor, as well as reducing the amount of sediment buildup inside that harbor mouth. A groin is used to preserve the amount of sand on a beach, although really what they do is make the beach crooked in this zigzag pattern. A groin causes sand to be deposited against the up-current side of the groin and causes erosion on the down-current side of the groin. You see a lot of groins on the Southern California coast. Here are some in what I believe is Malibu, and we can see sand is asymmetrically piled up against these groins. Here's another breakwater in front of a pair of jetties, also somewhere in Southern California, and the breakwater is just reducing the energy of the waves entering the harbor mouth. Whereas the jetties are protecting it from silting up. You can see the sand that's being moved by the longshore current is piled up against both sides of these jetties. Next up, we have barrier islands. These are long, low-lying islands that extend parallel to the shoreline. These look like a beach or a sand spit, and it is separated from the mainland by a sheltered body of water called a lagoon. These can form any of several ways. Sometimes the longshore current will veer offshore away from the actual shoreline, and this will encourage deposition and movement of sediment a short distance off of the mainland. Or a sand spit or baymouth bar can be cut off from the mainland by storm waves. Or remnants of sand dunes from when sea level was lower. For example, when sea level was lower, that exposed the continental shelf and all of that sand was blown up into sand dunes parallel to the coast. Then sea level rose, which inundated and isolated those sand dunes. Barrier islands can also form when waves drop sediment offshore because of a very shallow coast. Much of the east coast and Gulf Coast of the U.S. is covered in barrier islands. These protect the coastline from intense coastal erosion during hurricanes, and also to some extent from sea level rise. We can see some examples of these along the Texas Gulf Coast, as well as the south shore of Long Island in New York State. Moving on to coastal erosion and weathering, we have the same basic types that we've seen elsewhere. Physical erosion is dominated by abrasion, hydraulic action caused by waves, as well as salt cracking. Salt water will get into cracks or pore spaces in the rock and expand, which causes the rock or sediment to crack. You also get chemical weathering, the same usual suspects: oxidation, hydrolysis, and dissolution of ions. One of the primary coastal erosion processes is that of the formation of headlands and bays. So when we look down from above, we can see that differential weathering or erosion leads to an uneven coastline. Wave refraction then preferentially attacks the sides of headlands to restore a more even coastline. So you've got your resistant rocks and your soft rocks. Over time, these soft rocks will erode faster and produce bays. But wave refraction, the waves will bend around these headlands, and the waves will then crash into the sides of the headland, causing more rapid erosion along the sides of that headland. This produces a number of different formations. The headland is any piece of a shoreline projecting into the water, ocean, or a large lake. And on the sides of these headlands are where we get features such as sea caves, sea arches, and sea stacks. Because the waves are refracting and attacking the sides of the headland, waves often very powerfully impact the sides of these headlands, which can carve out caves, usually along weak zones such as joints or faults. Hydraulic action and abrasion will eventually enlarge those caves, and they may poke through and perforate the headland, forming a natural arch. But not all arches live forever, and they will eventually collapse, leaving behind a sea stack, or, after an even greater amount of time, a stump. The repeated action of waves against the base of cliffs causes those cliffs to erode and creates something called a wave-cut platform. The energy of the waves attacks the base of the cliff at the place called the wave attack zone, and this is the area that sees the strongest physical erosion. As your cliff gets undercut by the action of waves, the cliff will collapse, steadily retreating, leaving behind a platform which is a sloping rocky platform left behind as the cliff retreats. Oftentimes these will be exposed at low tide. On the lower right, we can see that wave-cut notch at the base of this rather unstable-looking cliff. Above that, we can see the wave-cut platform at the base of this sea cliff, where the cliffs have receded over time. Sea levels will change globally, either due to climate change, or locally due to isostatic or tectonic uplift, or subsidence of the land. That is the land surface rising or sinking. So what happens to the coastal area if sea levels rise or drop? A submergent or sinking coastline has features associated with rising water. Generally, these are depositional features. An emergent or rising coastline will have features associated with falling water. Generally, these are erosional features. So, for example, a submergent coastline will see a lot of estuaries, a lot of barrier islands and sand spits. In areas with a lower sediment supply, you will see flooded valleys. And in glaciated areas, you will see fjords, which are glacially carved valleys that have then been flooded by the sea. In an emergent coastline, you will see uplifted marine terraces, which I'll talk about in a minute, which are just wave-cut platforms elevated above current sea level. You also see more features like sea stacks, headlands, sea stumps, tombolos, and pocket beaches in between the cliffs. So what happens to a wave-cut platform or wave-cut bench if relative sea level drops, forming an emergent coastline? Well, you will get a platform elevated above the surface of the sea. Some of the best places in the world to see these features are in the Channel Islands National Park of California. These islands are surrounded by marine terraces, which are former sea levels, ancient wave-cut benches that have been slowly tectonically uplifted over time. Because the Channel Islands, located off the shore of Southern California, are in a very tectonically active area, the islands are constantly being tectonically uplifted. But at the same time, the ocean waves are constantly eroding cliffs. So we get marine terraces formed during interglacial periods, times like today when we are not in an ice age, and then during ice ages, sea level drops, but the island is still rising tectonically. So over time, these older surfaces are being elevated by tectonic action. At submergent coastlines, where the relative water level is rising, the mouths of river valleys become flooded, creating estuaries. We have tons of estuaries on the east coast, like Chesapeake Bay, one of the largest estuaries on the continent, much of which is less than 6 feet deep, even though it is a very large body of water to which numerous rivers drain in. And in glaciated areas, the U-shaped glacial valleys along the coastline become flooded, creating fjords. You find fjords in anywhere where tidewater glaciers are found as well. Fjords usually have very steep sides and a relatively flat bottom, that characteristic U-shape of glacial valleys. Some of the densest concentrations of fjords in North America are found in Alaska. This pictured fjord is in Glacier Bay National Park. And we've already talked about coral reefs in a previous lecture. In places where coral grows, a submergent coastline leads to the formation of barrier reefs and atolls. A classic submergent coastline is that of a volcanic island out in the ocean, which is constantly sinking under its own weight. As that happens, the coral continues to grow upwards and creates a barrier reef and eventually an atoll. Revisit the previous lecture on the subject if you need to revisit the topic. While atolls and barrier reefs are typically features found in submergent coastlines, in emergent coastlines you will find dead or beheaded coral reefs that are now sitting above the waterline where they are being steadily exposed and eroded. We can see some such cases here on this slide with fossilized corals from dry land. Florida contains many fossilized coral reefs that are above current sea level. And much of the island chain known as the Florida Keys are ancient coral reefs that were formed when sea levels were higher during the last interglacial period, before the last ice age. Coastlines are very complicated zones. We have a lot of great national parks along our coastlines, and there are many processes that occur, both as a result of wave action, as a result of erosion, and as a result of many other processes that occur with the intersection between water and land.